So the project we decided to do was finding the orbit of the planets with the law of orbits from Kepler's laws.
This is from me and Carly, and celebrity mention, of course, being Johannes Kepler, if that's how you pronounce his name. So, before we get into it, there's some things to look into. Obviously, the orbit of every planet is an ellipse, and it has the sun at one of the two foci. So that's just one of the things you're going to want to know is that the sun is one of the foci, and that there's obviously technically another one, but the main thing people obviously think about is like the planets revolving around the sun. The second thing that you can see is that with multiplying a planet's eccentricity by the semi-major axis, we can then find the foci, which is then what we are going to use to find the minor axis. So then we can graph the orbits of the planets, and we'll go into more detail on the next slide.
So our process is finding the foci, finding our minor axis, plugging in those numbers into our equation, graphing them, comparing the graph, and at the end we're going to calculate our error percentage. And then we profit.
So first off is Mercury, planet closest to the sun. Here you can see our process in the little written section. We've laid out a lot more and labeled a lot, but we start off by multiplying the semi-major axis with the eccentricity to then find the foci. All of these numbers being found from Wikipedia, but they're all from there to make sure we have the consistency. After that, we multiply the semi-major axis by 2 to find the major axis. Then we do c squared with the foci equals a squared, the major axis, minus b squared, which is what we're finding, which is the minor axis. Of course, after solving that, that gives us 0.770. We then put that into the equation, and you can see up here R's compared with Wikipedia's number, and here you can see the graph of the two
Ellipses.
Thank you.
This is actually our highest error percentage because you can see the red and the blue separately. On other ones like this one, you cannot see the difference. This is what we got for Venus. You can see they're very circular, and you'll notice as the graphs start to go on and the planets get farther away from the sun, the numbers go up because the orbit gets bigger because they're farther away from the sun.
Yes, the rings slowly get farther and farther away from the sun. So earlier you saw we were under 1. Now you see we're on 3. After on Jupiter, we're here at 10. It continuously obviously gets bigger and bigger. So it's just sort of the same process, comparing the two. At this point, because we're working on an astronomical scale, the difference is so minimal that until you start seeing the error percentage, it looks like it's two the same graph. And the reason these numbers are so low, like being in the tens or less than ones, is because we're working with AU, which is astronomical units, as we are using things on a literally astronomical scale. So then here at the last planet, we got from below 1 to now 60. And then here, we calculate the error percentages.
So our highest error percentage was in Mercury, and we had a little less than 2% of an error. And our lowest was Venus, which you can see is very, very small.
So we decided to calculate 4 error percentages because as I was working on this, I realized this is a lot like some of the chemistry labs I do. And I wanted to find out how far off our calculations were from the actual thing. We knew that they wouldn't be exact because when you're working on a scale so big and with so many different things taking place, obviously different things affecting the gravity, and just nothing like this is going to be perfectly the same thing. We wanted to calculate how far off our answer was from just using the numbers we had to find the numbers we didn't, instead of the actual measured and calculated numbers. So
That's it.
That's it.
Thank you.
Thank you.